The hydraulic system is the driving force for cranes and other heavy machinery. An integrate system composed of various interconnecting devices driven by hydraulic pressure. In this section, we will explain how each device interconnects with one another when operating the winch. First, the variable pump is driven by an engine, sucking hydraulic oil from the tank. The oil is then sent to the multiple control valve. At the same time, the gear pump sucks and delivers hydraulic oil to the remote control valve. The remote control valve is connected to the levers in the operating room, where the operator selects which outlet port to send the oil. Hydraulic oil from the remote control valve's outlet port is sent to a connecting pilot port of the multiple control valve, which then moves the spool. Based on the position of the spool, an outlet port is selected, and oil is then sent to the variable motor's counterbalance valve. Hydraulic oil passes through the counterbalance valve and heads towards the variable motor, where its pressure then rotates the motor. The drum rotates along with the motor, hoisting or lowering the load. If the load of the motor is too great, the relief valve opens, relieving pressure to the tank while maintaining the circuit pressure under a set value. The variable plunger pump is the driving force for the motor and other actuators, which highly pressurizes and delivers hydraulic oil from the tank. The pump is composed of a casing, shaft, cylinder block, plunger, swash plate, valve plate, and other components. As the shaft rotates, the plunger strokes along the swash plate, sucking and delivering hydraulic oil. The delivery flow can be adjusted by altering the inclination of the swash plate. The delivery flow is controlled by the regulator. The regulator controls the pump output to correspond with the engine output by adjusting the delivery flow. Next, we will explain how the regulator decreases the flow rate. When the delivery pressure of the pump P1 or of a companion pump P2 increases, the pressure moves the compensating piston, pushing it against the compensating rod. As the compensating rod is pushed, the lever rotates, moving the feedback lever, which in turn moves the spool. Also, the delivery pressure of P1 passes through the spool and pushes against the larger side of the servo piston. As the servo piston moves, the inclination of the swash plate decreases, reducing the delivery flow. Next, we will explain how the regulator increases the flow rate. When the delivery pressure of the pump P1 or of a companion pump P2 decreases, or when the pilot pressure is released by the power increasing control system, the compensation rod and piston are pushed back by their springs. As the compensating rod moves, the lever rotates, moving the feedback lever, which in turn moves the spool. As a result, the pressure within the larger side of the servo piston is released through the tank port, which then moves the servo piston. As the servo piston moves, the inclination of the swash plate increases, increasing the delivery flow. The gear pump highly pressurizes and delivers hydraulic oil from the tank, providing pilot pressure for remote control valves. The pump is composed of a casing, a drive gear which is rotated by an engine, an idle gear which is driven by the drive gear, and other components. While the gears rotate within the casing, a vacuum is created at the pump inlet, where the gear teeth separate, forcing hydraulic oil into the inlet from the tank. The gears rotate, pushing the hydraulic oil to the outlet to be delivered. The remote control valve directs hydraulic oil to different ports to act as pilot pressure. The valve is composed of a casing, control levers, discs, push rods, springs, spools, and other components. The spool is equipped with two types of springs: a return spring to return the control lever, and a second pressure balance spring. When the lever is operated, the push rod is pushed down, moving the spool. This allows for hydraulic oil from the pump port to be directed to either port A or port B. Both ports are connected to the pilot ports of the multiple control valve. As hydraulic oil enters the pilot port, it pushes against and moves the multiple control valve's spool. This gradually creates a second pressure. This second pressure is transmitted to the remote control valve's spool and pushes up against the balance spring. This causes the port to close, stopping the flow of hydraulic oil, and prevents the multiple control valve's spool from moving. Similarly, by using a balance spring to balance out with the control lever, it is possible to control the second pressure with the stroke of the control lever. As a result, allowing the operator to move the multiple control valve's spool freely. The solenoid valve electrically changes the circuit of the hydraulic oil. The valve is composed of a valve body, spool, solenoid, and other components. The solenoid is constructed of a coil and of a moving and fixed iron core. When electricity flows into the coil, the fixed iron core becomes magnetized, attracting the moving iron core to it. When the electricity flow is turned off, the spring pushes back the moving iron core. By controlling the flow of electricity, the spool can be moved using a solenoid. This allows for the flow of hydraulic oil to be controlled. The multiple control valve redirects the highly pressurized hydraulic oil from the variable pump, using the pilot pressure received from the remote control valve. The valve is composed of a casing, spools which redirect the hydraulic oil, return springs which return the spools to their original positions, and other components. The passages for the hydraulic oil are branched off as so. From within this, hydraulic oil passes through the valve to a port based on the position of the spools. When all the spools are centered, hydraulic oil from the pump port passes through the central passage and each valve passage exiting to the tank port. The pilot port of the multiple control valve receives hydraulic oil from the remote control valve. Pilot pressure from the remote control valve moves the spool and redirects the hydraulic oil from the pump port to either port A or port B. The spool continues to move until the pressure applied to the pilot port balances with the return spring on the opposite side, changing the opening area, which in turn adjusts the flow rate. The relief valve is a safety valve, which releases pressure to the tank when pressure within a hydraulic circuit exceeds the set pressure. The valve is composed of a valve body, pilot valve, poppet valve, and other components. Normally, the poppet and pilot valve remain closed, preventing flow through the valve. When the set pressure is exceeded, the pilot valve is pushed open by the pressure, connecting the circuit with the tank port, allowing for hydraulic oil to flow through. As hydraulic oil passes through the small orifice, the oil's pressure drops. This causes the pressure in chamber B to decrease. Due to the difference in PA and PB, the poppet valve opens and provides relief to the circuit. As pressure decreases due to relief, the pilot valve's spring forces the pilot valve to close, and the pressure in both chamber A and B become equal. As the pressure difference between the chambers decrease, the poppet valve's spring forces the poppet valve to close and ends relief. By repeating this process, pressure can be controlled within a set value. The counterbalance valve acts as a braking valve for the hydraulic motor when lowering loads or moving downhill. The valve is composed of a casing, check valve, spool, and other components. When a load is being lifted, hydraulic oil from the pump passes through port A, pushes open the poppet on the check valve, exits through port D towards the motor, and rotates the motor. The returning oil from the motor then passes through port C and B and returns to the tank. When a load is suspended, the circuit from the motor to the counterbalance valve is closed by the spool. This causes internal pressure to accumulate due to the weight of the suspended load, which holds the load in place. When a load is being lowered, hydraulic oil from the pump is sent to the motor and passes through ports B and C. With a circuit between ports D and A closed, pressure accumulates in the inlet side. As pressure builds, oil passes through the pilot passage of the spool and applies pressure to the side of the spool. This pressure gradually overtakes the spool spring, moving the spool. As the spool moves, the circuit between port D and A opens. This allows the motor to rotate, lowering the load. At this point, the motor will attempt to rotate quickly due to the weight of the load. However, pressure decreases in the inlet side, closing the spool. As a result, internal pressure builds between the motor and counterbalance, holding the load. By repeating this process, the load can be lowered smoothly. The variable plunger motor is used in the hoisting and operation of the crane. Its rotational force is controlled by the hydraulic oil pressure, delivered from the variable plunger pump. The variable plunger motor is composed of a casing, shaft, cylinder block, swash plate, plunger, valve plate, and other components. In general, when a force is applied from above on an inclined surface, a lateral force is created, sliding the object downward. In a variable plunger motor, the pressurized hydraulic oil creates this lateral force by using the cylinder and plunger. When cylinders are placed in a circular pattern around a shaft, a continuous downward lateral force is created. This creates a rotational force. By adjusting the inclination of the swash plate, the rotational speed and torque can be adjusted.